All right, we're looking at 0654, summer 2019, paper 6.1, question 6, which is the second of the physics questions. We're asked to measure the length. Again, as in a similar problem, you're being asked just to use your rulers, folks. Okay, I'll just put mine upside down like this. Okay, and measure. Okay, you will notice that your answer will be slightly different to that on the mark scheme. That's the reason for that. Again, is the scaling problem. Don't worry about it. It takes about 1 millimeter away. Now, the key point, I think we can all use a ruler. Pay attention to this, please. Okay, I almost didn't pay attention to that. You'll notice here, I wrote my distance here. I measured it, length 3.4 centimeters. Well, what I didn't do was turn it into millimeters. I then, just as I was leaving the question, noticed that the question was asking for millimeters. Please remember to turn that answer into that way. Okay, if you left it as 3.4 centimeters, they have told you millimeters. It's debatable as to whether you would get the mark. Okay, you then need to use your number. Well, you'll see why again. If I don't turn this into millimeters, I'll have some problems later. Okay, you're going to use your numbers to do some calculations. All right, you're told L2 is 95, and therefore all you need to do is take your L1 value from up at the top and find the difference between them. 95 to 34, 61. Okay, again, mark scheme would say 60 on here because their value of L1 was 35. That doesn't matter. All right, do not worry. We're only interested in the process here, not necessarily the values. Though that scaling error would not be on your exam, so it's nothing to worry about. Okay, calculate the spring constant. K, as we know, is F over E. They're using E here. We use X. Doesn't matter. K, therefore, is 3, which we're told, newtons, divided by 61, which is going to give you 0.49049, okay, 0.0492, which is 3 significant figures. Okay, good idea to keep things to 3 significant figures. In the mark scheme, it's a much nicer number. Unfortunately, that's not what we're looking at. Okay, let's just keep the diagram here. You're then asked to make sure that you're doing things, to avoid errors. Okay, now again, a lot of students start talking about using different equipment, etc. Okay, fine, there are suggestions that we could make, but really we don't want to reinvent the wheel here. We just want to do the experiment in a better way. Now, obviously what you're going to do is you're going to use a ruler. Okay? Now, there's loads of suggestions about this, okay? Firstly, obviously, I need to make sure that ruler is close, all right? Measuring, I also need to use a straight ruler, but I think we can assume it's straight. Measuring at a distance is never going to be good, okay? When you're measuring, if I was measuring here, I need to make sure my eye is here, okay? You never measure with your eye at the top or at the bottom. This is something called parallax, okay? And it will mean that your measurements are wrong, okay? And that's the most meaningful one of these for me. There's loads of other things. Put this ruler in a clamp, okay? Use something right-angled, a set square to make sure that that ruler is vertical, all right? So the ones that I went for, okay, were the two: view with your eyes perpendicular to the ruler, okay? What that means is avoiding that parallax error, okay, and also use a clamp stand to hold the ruler in place. Really, we're looking for basic experimental suggestions here, okay? And unfortunately, we don't know a lot about the technique used by the student here. However, we've got to assume that they've got some good equipment there, some basic equipment that we can then add to. Okay, I really think this question we're going through the motions now, because all we're doing is just doing some simple calculations. All right, first one, we've got a stone now, and we're asked to calculate the mass of the stone. You're given the equation. Notice, really, I don't need to read any of this stuff. The only thing I need to read is this. Okay, so if you're in a hurry, all right, I wouldn't encourage you to do this, but if you're in a hurry, there's something to be said for just going straight in at the questions. They're 1 mark calculations, not much can go too wrong. Main thing to pay attention to, we've got 100 times K times EA. EA is up here, it's the extension of the spring. Okay, and K we had to take from our previous question, which was our 0.0492. Remember that if you got that wrong in the first place, you're only going to get punished once as long as your technique is correct. All right, so I got this. I got a mass of 221 grams. We're then got a new situation where we put this thing in water, in water, yes. So we notice that that extension decreases. We've got something called EW, the extension in water. All right, we're going to see what we do with that. We are told that we can find the density of the stone just by taking our two EA and EW. We're told EA, we're told EA, and we're told EW. It's just a case of calculating. All right. Again, we're asked to calculate the volume of the block of metal. Well, this is a cuboid. We're not told an equation this time. I think it's assumed that you know how to calculate the volume of a regular object. Okay. We're doing 8 times 2 times 1.5. Yeah, and that's just our 24. We're then told in part 2, yeah, we've got a scale and we've got our block of metal in there. Notice this scale is not 100% easy to read. That's relevant for later. It tells you just now to read the scale to the nearest 1 gram. So even though part of you might be going, okay, hang on a minute, that looks like it's somewhere between the two. All right, it's definitely closer to 65, so I'm going to go for 65 there. All right, but that fact that they've said that is almost a lead-in to what they actually want you to discuss in the next questions. All right, firstly, you're asked to calculate density. You're told the equation for density. All you have to do is take your values. I think the only thing that could go wrong here is if you mix them up. Okay, a good point here is actually on that point, the density of water, yeah, is equal to 1. Okay, if you're working in grams and centimeter cubed, it's equal to 1. That may be an important number for you to think about. I really should call it 1.0, but I'm being lazy. Okay, is that if our object is for it to sink, and you expect your density to be greater than 1. If it is a greater density than the density of water, then it's going to sink. That is going to be important for your calculation because you can then use that to check this value. Okay, is it greater than 1? Fine, I've not made a mistake. Last bit, an improvement to the equipment the student has used. Notice there, an improvement to the equipment the student has used, specifically in F. Now, if you go back and look at F, the student hasn't used any equipment apart from this. Yeah, there's no equipment in F. All right, you've not been given anything. You're clearly being told to think about this guy. Well, what did we say before? We noticed that this value is somewhere between the two. Now, what would make that better is obviously if I had a scale which read, for example, to half grams. All right, instead of just 64 and 65, if it could measure 64.5, then that would give me a better, more accurate answer. Okay. So you need scales with a higher precision. Adding that scale would allow higher precision. And they could also just use digital scales. Digital scales are scales which are generally able to give you to 0.1, 0.01 of a gram, and so they will allow you to get more accurate measurements.